In this lesson, we're going to be looking at trigonometric identities and how we might use them. All right, here's some fundamental trigonometric identities. And what that means is these are given to be true. So we've already seen some of the reciprocal identities. Well, we've seen them all, actually. We've seen the reciprocal identities in that the sine of theta is equal to 1 divided by cosecant of theta. Likewise, cosine of theta is equal to 1 over secant of theta, as well as tangent of theta is equal to 1 over cotangent of theta. We can kind of think of doing the reverse as well. Cosecant of theta is equal to 1 over sine theta, secant theta is equal to 1 over cosine theta, and cotangent theta is equal to 1 over tangent theta. So these are the reciprocal identities that we have some prior work with. All right, the quotient identities. These are all given to be true statements. Tangent of theta is equal to, on the unit circle, it was y over x. You might remember tangent was y over x. Well, y is associated with the sine of theta, and x is associated with the cosine of theta. So tangent of theta can be rewritten, if need be, as instead of tangent of theta, as sine theta over cosine theta, as well as cotangent of theta is your x over y on the unit circle. X is corresponding with cosine of theta, and y is corresponding with sine of theta. All right, so we've got the reciprocal identities, the quotient for fraction, that's what we have here, identities, and then we have the Pythagorean identities. All right, Pythagorean, when you hear that word Pythagorean, you might want to think about the Pythagorean formula, a squared plus b squared equals c squared, meaning that I would kind of connect to Pythagorean, I would think of squares, not cubes, fourth powers, but Pythagorean formula has the square powers. And you can see in these Pythagorean trigonometric identities that we have squares. So these identities work only if the exponent is 2, not any other number. I think my hole is punched off here, so I'm going to rewrite this. So sine squared of theta plus cosine squared theta is given to be equal to a value of 1. So if I know an angle is, just say, I don't know, I'll make it up, 45 degrees. Let's say that theta is 45 degrees, and I find the sine of 45 degrees and then square that number and add it to the square of the cosine at that same angle, those values would add and give us an answer of 1. Something that we want to do with the Pythagorean identities is we want to change their forms. We want to look at other formats. So if this is given to be true, which it is, sine squared theta plus cosine squared theta equals 1, then let's do some rearrangements here. In our work that we're about to do, it might be necessary for us to know what sine squared theta is equal to. So I'm actually going to kind of rearrange this Pythagorean identity. I'm going to move over the cosine squared theta to the other side of the equation, isolating sine squared theta. So if this equation is given to be true, then it must be that sine squared theta is equal to 1 minus cosine squared theta. And one final arrangement is, what if we wanted to get cosine squared theta by itself? Then that would require us to move over sine squared to the other side. So given this Pythagorean identity, we can rearrange it a couple different ways depending upon our use, our needed use in the future. All right, here's another Pythagorean identity. It says that 1 plus tangent squared theta equals secant squared theta. All right, well, what's another arrangement of this true identity? Well, let's say I wanted to move over tangent squared theta. So that would leave 1 equals secant squared theta minus tangent squared theta. Is there another arrangement of this true identity? Yes. Then we could also say tangent squared theta equals secant squared theta minus 1. So you go ahead and do some rearrangements here for this given true identity. So again, when I think about the Pythagorean identities, I think about a power of 2, not a power of 3, 4, 5. This is only true. These identities are only true if the exponents are 2. It would not be true to say that 1 plus tangent cubed theta equals secant cubed theta. And then also, in addition to seeing powers of 2, I also see that in each 3 of these Pythagorean identities, I also have a 1, a value of 1. Okay, so what do we do with these identities? Well, we can do several things, but what we're going to focus on here is we're going to focus on taking a given problem, which in all 4 of my examples down here, these are given equations. They're not expressions. Equations meaning that I see an equal sign. We're going to use the trigonometric identities to transform one side of the equation into the other. We're going to transform one side of the equation, either the left or the right, and make it look like what's on the other side of the equation by involving these identities. Now, this right here is just telling us that the angles that we're going to be working with are values between 0 and pi over 2. So really, this restriction right here isn't going to have any bearing on the work that we do. This is just a technicality for these types of problems. Sometimes it's important that we know what restrictions we have depending upon what we're finding, but for what we're about to do, we're just told that the angles we're working with are acute, less than pi over 2. All right, so back to the objective. Use the trigonometric identities above to transform one side of the equation into the other. All right, when I look at this first example right here, I can see that on the left-hand side of the equation, I've got a multiplication of cosine of theta, whatever value that is, times the secant of theta. And they're telling me that cosine of theta times secant of theta is supposed to equal a value of 1. So we're trying to do a little trigonometric proof. We're trying to prove that this product will equal 1. I usually, when I'm trying to transform one side of an equation to make it look like the other, I usually start with the more complicated side. And obviously this is more complicated than 1. So I start with a complicated side and I think about all my identities. And I go, well, cosine of theta, got it, is equal to 1 over secant theta. I look for cosine of theta in the 3 different types of identities. Okay, and then I look at secant of theta and I go, oh yeah, secant of theta right here is equal to 1 over cosine of theta. So that's equivalent. So what I'm going to do down here is I'm going to keep the cosine of theta. I might put that in parentheses, not necessary. But where I see secant of theta, now this is times, well, I know that secant of theta from above is 1 over cosine of theta. And then I'm going to put the equals here. And I'm going to put the 1 here. And I'm going to put a question mark here because I have not yet made the left side of the equation exactly into 1. So I'm not working on both sides of the equation. I'm completely working on one side of the equation, doing some work down here so that eventually what I end up with when I simplify is I end up with what's on the other side of the equation. Well, this is just a simple multiplication problem. I could put cosine of theta over 1. When I'm multiplying the cosine of theta value, whatever that answer is, times the cosine of theta, those are going to divide out. So I'm left to multiply 1's on top and 1's on bottom. So I just get 1 equals 1, check. I've just proven that cosine of theta times secant of theta is actually equal to 1. So I'm not solving anything, I'm just proving that one side looks like the other. All right, I'm going to drop down here and do this example next. Okay, for me to use the trig identities to transform one side of the equation into the other, first thing I do is I look for the more complicated side. To me, it looks like it's the left-hand side of the equation. I see I'm multiplying tangent theta times cosecant of theta, and I'm supposed to get secant of theta. So I kind of study what's going on here, and I go, okay, tangent of theta, I might rewrite this. I think about cosecant of theta, and I'm thinking, okay, cosecant of theta is equal to, what is that, 1 over sine theta? Yep. So bring down the equal sign. That just keeps coming down. And remember, we always want secant of theta. Always keep your eyes on the prize, like we're looking for secant of theta. And I'm going, well, I can make this tangent theta over sine theta. but I really don't see anything up here that's going to help me get to secant theta. So I'm going, well, maybe I should change tangent theta. So I'm actually going to erase tangent theta. I'm going to use the quotient identity. Remember, tangent is sine theta over cosine theta. Would that help if I put sine theta over cosine theta? Well, maybe. I see that now I can divide out the sine theta values, and I'm left with 1 over cosine theta. Bring down the equal sign, bring down the right-hand side of the equation. You never change the other side of the equation. Well, wait a minute. That's a reciprocal identity. Looking back at the top, 1 over cosine theta is equal to secant of theta. So working down, I'm going to just say secant of theta, bring down the equals, is equal to secant of theta. I might put a question mark, not a big deal. But your work down one side of the equation on one side of the equal sign, your work down mathematically, trigonometrically, should result in your arriving at the same answer that you had, expression that you had on the other side of the equal sign. It takes practice. Some of them get complicated, and there's certainly multiple ways to transform one side of the equation into the other. So if you thought of a different approach, continue with it, because it's probably going to result in your getting secant of theta anyway, but just by going a different path. Remember, there's many ways to get to school. You could drive one way one day and one day the next, but you're all going to end up at school. Okay, so same thing with these little trigonometric identities and transforming an equation. All right, let's look up here at this example. I certainly think that the more complicated side is the left-hand side of the equation, and it's saying that all of this work right here should result in a 1 answer. All right, so I'm taking a look at what's happening over here, and the parentheses suggest to me that maybe I should FOIL. I don't know if I would change secant theta to 1 over cosine just yet. Don't know if I would change tangent of theta to sine over cosine just yet, because then I'm going to have to get a common denominator. I think that a binomial times a binomial suggests that we FOIL. Sometimes I have a entry point and I think, okay, that's going to work, and it doesn't. I have to go back and erase and start all over with a different approach. But I'm going to try the foiling method first. So secant theta times secant theta is going to give me secant squared theta. And already I'm thinking Pythagorean identities because I see that power of 2. Outside is minus secant theta times tangent theta. All right, inside is going to be plus secant theta times tangent theta. Oh, that's right. These are going to cancel, because this is sum and difference of two like terms. The secants are the same, the tangents are the same. I have a plus and minus. So that's right. These two terms are going to cancel. And then the last terms give minus tangent squared theta. Remember, we're at the equal sign. Bring down the 1. If you want to put a question mark, that's fine. We still have more work to transform this into a 1. All right, well, let me clean this up. Now I have secant squared theta minus tangent squared theta. Got an equals, question mark. Is that equal to 1? Well, I'm thinking Pythagorean identities because I see the squares. I know which one I want to look at, this Pythagorean identity. Let's look at a rearrangement. Is there somewhere as one of the rearrangements the expression secant squared theta minus tangent squared theta? Remember, these are given as true, so I can use these in my proof for my work. Well, yeah, right here. Secant squared theta minus tangent squared theta is equal to 1. So that means that because I have this expression, I can replace that whole thing. This whole thing is equal to 1. So I can say 1 equals, got the equal sign, 1 equals 1. That is true. All right, continue our work of transforming one side of an equation into the other. This looks like the more complicated side. I'll start there. Okay, well, there's no suggestion to me that I should FOIL because I don't see sets of parentheses. Whew. I've got a fraction. I want to get to cosecant squared. I am thinking Pythagorean identities, maybe. Maybe not. We'll see. That's on my radar. I'm not multiplying. I need to get rid of this fraction. Let's use the break apart method. I don't know. There's several things you could do. You could change tangent theta to sine over cosine, cotangent to cosine over sine theta, but then you'd have to get a common denominator. I mean, that certainly probably could work. It just might take us longer. What I see right here is, let me break apart this fraction. Let's kind of share the love, if you will. When you divide by a monomial, one term, tangent of theta, I can take every term of the numerator and put it over the denominator. So I'm going to break it apart and say, okay, I know mathematically this is true, that I could separate this. So I could put tangent theta over tangent theta, go to the plus sign, and put cotangent theta over tangent theta. And that's supposed to equal cosecant squared theta. All right, then I come back here and focus my attention. What more work can I do? Well, I see that that's equal to 1. So 1 plus, and I still got this cotangent theta over tangent theta fraction, and that's supposed to equal cosecant squared theta. Remember, you're only working on one side of the equation. All right, well, I'm thinking Pythagorean identities because I see a square on a cosecant and I see a 1. So let me go back up there and take a peek at those. So here's that Pythagorean identity. Now, I need 1 plus this right here. If it could be changed correctly into cotangent squared, then I know that that's equal to cosecant squared. So I need to focus my attention on the fractional part of where I'm at in my work to see if that is equivalent to cotangent squared theta. So I need a little more room. I'm going to come up here. So, okay, let's see what we can do. 1 plus. All right, on this fraction right here, let me rewrite this fraction and make it cotangent theta over 1 times 1 over tangent theta. So, and we're at the equals, question mark, cosecant squared theta. All I did is unstack this fraction right here by making it a multiplication problem. If I put it back together by multiplying, I'm going to get back here. Well, that's going to be helpful. 1 plus. Remember, we need a cotangent squared. So I've got a cotangent theta. I'm going to disregard the 1 here. But right here, that's a reciprocal identity. 1 over tangent of theta can be replaced with cotangent theta. So we're going to do a substitution here times cotangent of theta. Question mark equals cosecant squared theta. Well, now we're just multiplying two of the same values together. So this is 1 plus. This is going to be cotangent squared of theta. And that does equal, or it's supposed to equal, cosecant squared theta. Yes, I am at the Pythagorean identity, but remember, we want to take and make this whole side equal to what's over here. So then I'm looking back up at this identity going, well, I know that 1 plus cotangent of squared theta can be replaced or substituted with cosecant squared theta. So by a given identity, Pythagorean identity, we can replace that with cosecant squared theta, definitely equals, and we always only brought down cosecant squared of theta. That's a check mark. All right, doing this type of work does just take practice, and so that's what we're going to be doing next, is just doing some more practice of transforming one side of the equation into the other.